good? Awesome. All right, so we're going to talk physics. We're going to talk physics today. It's going to be awesome. Yes. So we're going to move into momentum. And you'll see as we go through today a lot of similarities between what we learned in energy and momentum. Okay, there's a lot of analogous situations that you're going to see. We're going to talk about this thing called impulse, and then momentum, and we'll talk about why momentum it's super powerful, but it's also kind of weird at the same time. And then we're going to come back to an old friend that we know and see how we already know it's really powerful, and now it's even more powerful. So we'll get to that. But to start, I got them back, and I've got 2 of them.
How much bowling balls does she have?
I just got 2, but I do have a full bocce ball set if I needed more large bowling ball type items. So, and if I really needed to, Mr. Murphy has his own set. He was like a big bowler back in the day. So he literally does have his own bowling ball set. You know you're into bowling when you own your own bowling balls. All right, so 2 balls, right? Same height, okay? For all intents and purposes, assume this is at the same level as the table, okay? I know it's taller, the pillow's taller, but it's at the same height. Imagine the same height, okay? So here. All right. We're going to assume they are, right?
Make that one a little higher.
No. All right, so balls up here, same height, okay? I'm waiting for this table to break one day. One more time, okay? One more time. Oh, it's so amazing. Okay? So here's what I want you to do. Based on dropping these 2 bowling balls, I want you to figure out 2 minutes with a partner, or actually by yourself. I'm sorry, no partners. By yourself, no talksies. What is similar about this situation, and what is different? And make sure you're using physics vocab, all right? Words that we use that are related to this class, okay? So, we have taken our 2 bowling balls. What? Right? 2 bowling balls, same height, fall to the same level. So tell me, what is similar about the 2 balls? Okay, so the height is the same, right? The initial height, the height is the same. Olivia?
Potential energy.
The potential energy is the same, yes. Jared, were you about to say that? Okay, what else is the same? The final, typically we kind of say the height is like the full thing, but yep, down. All right, so the final speed, so V sub F is the same. What about V sub I? V sub I is the same also, right? Anything else the same? The mass, yep. Okay, what else? Kinetic is the same, yeah. U and I, right? I'm sorry, final and initial. They're both the same, right? Okay. U is potential, right? Someone say gravity, right? The force of gravity is the same on them. So, right, the mass is the same, gravity is the same. Okay, so essentially the weights are identical, correct? Anything else we could say is similar about these? There's one that's really big, super fundamental, like base level fundamental quantity that's really important. Jared? No? You don't want to throw it out there, just see what happens, see if it sticks?
I was about to say acceleration, but
it's gravity, right? There's one, like I said, there's one term, one quantity that's really important, really basic. Not momentum. No, we haven't talked about momentum. That's not basic. What? No, we don't want magnitude. Magnitude is amount, remember? All of these, not the direction, but the direction is the same, right? Magnitude for all of these things have magnitude, Miss Hall. One thing, there's one that is like really basic. Time.
Wow.
And it's the time of flight, right?
I wrote that down. I didn't even know it. We're done for. You almost had it.
So it's the time of flight, right? The time they're in the air, that's the same. Awesome. Okay. So, what's different? Sure.
They decelerate.
Okay, so deceleration is different. Okay. What else is different? Are you raising your hand?
Yeah. The energy is converted with different magnitudes of quantity. If there's more sound energy in the one that's speed.
Well, it's called transformation. Right, so the energy transformations are different. Right? One of them has a very large transfer of sound-to-sound energy, and one doesn't. Okay. Anything else? Any other? What do you think?
I just wanted to say the moon is the difficult time.
Well, try it. Try me.
Well, like the ball on the pillow like bounced before it rests, like landed at rest or whatever.
Okay. All right. So there is something to when it hits the table, right, and the pillow. There's definitely something to that. So how could we characterize that in physics vocab? Any idea? Right? Think about imagine this was you. Right? Which one would you rather be? Why the pillow? Less impact, softer impact. How could we use that now in terms of physics things? If we're talking about impact, what word would be used? Force, right? Does that make sense, right? So the force of impact is different in both cases, right? What about the other? There's one more that's also important that has to do with the force as well, but watch what happens to each ball. Right? If this bounces, right? But what else about these? This just hits, and that's it, right? What happens to this ball? Right? When it hits, this is very sudden, right? This one takes what? More time. So the time of impact is different as well. Right? Awesome. Oh. Kelly Green. Here you go. These are going to be two important ones right there. Those are going to be two important terms right there. Okay? So I want you to keep this stuff in mind. Now, we're going to come back. We're going to revisit an old friend of ours now. Oh. Yes, yes. F equals ma. What is this? What's this called? Newton's second law. No more Panic at the Disco. So, the disco is nice and calm now. So, I'm going to take this Newton's second law, right? F net equals ma, and I'm going to just rearrange it a little bit. And Isaac Newton, the way that he explained the second law is a little more general than how we've been dealing with it. All right? We know that acceleration is v sub f minus v sub I over t. Right? So I'm just going to make that substitution in there. Okay? And then v sub f minus m v sub I. So all I've done is I've just distributed the t to the other side, and then I pushed the m through. Okay? Does that make sense? Pretty simple. This, if we change it just a little bit more, I'm going to leave this piece right here, and I'm going to kind of branch this over here. Not yet, I'm sorry. Not yet. So we can now take this equation and we can define some of these terms. Okay? That F net times time is what we call impulse. Okay? That's the equation for impulse. We call impulse capital J. We can't call it capital I because capital I stands for something else. So impulse is equal to force times time. Momentum is mass times velocity. Momentum we call P, lowercase p. Okay? So if we are looking at this equation, okay? If we are looking at this equation, we can rewrite it as J is equal to delta P. So impulse is equal to the change in momentum. Does that make sense? Right? So impulse is equal to the change in momentum. So let's go back to what we know about work and energy. Because this is a very analogous situation. Right? Analogous means they're similar, right? They're related to each other. Instead of impulse causes a change in momentum, we know that work causes a change in energy. Right? Very similar situations. Right? W equals the change of kinetic or the change of potential or anything like that, right? Same ideas. That's why we take these two units and we kind of squish them together, because they're very similar ideas and topics. Okay? This equation is going to call the impulse momentum theorem. Okay? So if we go back to here for a quick second. We've got F net equals M V sub F minus V sub I over T. If I distribute this M through, I get M V sub F minus M V sub I over T, right? This is delta P, correct? Right? So very simply, Newton's second law is really, in terms of big views, Newton's second law is actually describing how momentum changes over time. Right? That's still F equals ma. We just kind of changed it just a little bit. We didn't do anything big, right? We didn't do anything big to it. A lot of times, once you get into like higher level physics, like I didn't actually see this until my junior year in college when I took analytical mechanics. They started describing this, right? They just started describing Newton's second law as this, and actually with calculus. So it's actually like instead of saying delta P, they would call it the derivative of P. But that's Newton's second law. We didn't do anything big, right? We just plugged in, we just substituted one thing in and put it together. So I think it's really cool that we took what we know of forces and one little thing, and now we see the relationship between force and momentum as well. Right? It's pretty cool. It is cool. Sydney doesn't think so. All right. So let's define a few things. From looking at the impulse momentum theorem, we know that impulse is what? What is impulse? Change in momentum, right. And let's think about it this way, going back to energy and work. If you don't do work, what doesn't change? Energy doesn't change, right? If you can't say don't do impulse. But if you do not apply an impulse, you don't experience an impulse, does your momentum change? No, right? So you need an impulse in order for it to change. And you need a force, right? You need a force applied in order for momentum to change. So remember, momentum causes things to speed up or slow down, accelerate. Okay? And that's when you get your momentum. Now momentum, before we get to that, I'm going to skip back up here. We know impulse is force times time. Okay? So here's what I'd like you to do. 2 minutes with a partner, using this idea of momentum. Why are airbags a good thing in a car crash? Go. Chomping at the bit. Fire away, Amanda.
It increases the time of impact, which decreases the force of the impact, so the change in momentum is decreased.
You had me until the end. You had me until the end. Jared?
The change in momentum stays the same. It's just whether or not the time is increased, that means the net force decreases.
Right. So no matter what, airbag, no airbag, your change in momentum is the same, right? You're going from some speed to zero, right? No matter what happens, okay? Does that make sense? Okay. But what you can play with, if we're thinking about, right, impulse is a change in momentum, this has to stay the same number. But this FT can be played with and still keep this number the same. Right, so airbag, you hit the airbag. You know how an airbag works? Goes out. You know it doesn't stay there, right? It deflates as you hit it, right? So that because if it didn't, you would probably bounce off the airbag and then bounce off the headrest, and it would be like ping pong going back and forth, right? And that would probably be worse, all right? So we know that the change of momentum is the same in either case, airbag, no airbag. But as you hit it, as it deflates, you go with it, right? It's kind of like hitting that cushion, because then you're slowing down, and essentially you're riding the pillow as it goes. So this number, the time of impact becomes very large. This number has to decrease in order to keep the change the same. Right? Does that make sense? So, quick story. The big thing with momentum, and I had a really hard time with this with momentum before, really until I got into later on in college, was exactly what momentum is. Right? Dallin, real quick, look up for me the definition of momentum. Work your magic.
You didn't bring the desktop today.
He didn't. Yes, Dallin didn't bring the desktop today. So you're going to get the definition of what's that?
Is this the quantity of motion of a moving body measured as a product of its mass and velocity?
Awesome. So you guys all totally understand it now, right?
No.
Yeah.
Right? So you look it up. He just looked it up, right? It's a quantity of motion, and it's the product of mass and velocity. Thank you so much for defining this idea with an equation. Right? Thank you. That is, I'm so glad that literally every physics book does that.
Tell me, you know how to say that word?
No, I don't. Impetus gained by a moving object.
An impetus, right? So essentially, momentum, it's very powerful, it's very useful, but it's really a made-up concept to help explain something. Right? Time is time. Time's very simple, basic, fundamental quantity. So is like distance and velocity and acceleration. Momentum, they were like, hey, we see this kind of this action occurring, and we need a word to describe it. Let's use momentum. Okay? The best way that me, my buddy, and one of my college professors could define momentum would be as mass in motion. Okay? Momentum is best described, or as best that I can describe it as, is mass in motion. Okay? Does that make sense? Right? So if you're not in motion, if there's mass is not in motion, you don't have momentum. Okay? Sid?
So is essentially like any of the concepts of momentum?
Not essentially, definitely. Yep. And also think about the equation of momentum. P equals mv. That v is 0, no momentum, no p. Okay? The unit for momentum. It's mass times velocity. Remember, the Newton? The Newton is actually like the kilogram meter per second squared, right? But rather than writing kilogram meter per second squared, you call it the Newton. makes life a little easier. Clearly, whoever worked on momentum was not that important because it stays as the kilogram meter per second. Maybe we'll call it one day the Gaudettes or something, something like that. Okay, so this is the unit for momentum. Now you know how we have that impulse momentum theorem, right? An impulse causes a change in momentum, and we had the work energy theorem. Do work, it causes a change in energy. We have those analogous situations. The other analogous situation that you guys are going to work on now is we have conservation of energy. Maybe there's conservation of momentum as well. Okay? So what you're going to do is I'm going to give you this assignment, and you're going to work on a FET that has to do with collisions and seeing if there is really a thing of conservation of momentum. All right? So you can use your computers, you can use the laptops over there. Unfortunately, you can't use the iPads because this simulation right now is a flash simulation. It's not something that they've gotten to in terms of making it more useful. Okay? That make sense? Good? Awesome. Let me give you that.